desk for chairs set up, and making sure there's booze in our first ever during the last 2 years in-person seminar. So thanks everyone. When you're done, go out onto the deck, take your masks off, have a drink, enjoy yourselves. It really is a momentous occasion. We also got to remember how special we are in regards to the fact that not everyone is to the point where they get to have this opportunity. So I think we should just relish in the fact that we have great personal scientific interactions and discussion and discourse, and so I think we should just take advantage of it and be good citizens and just enjoy it. And with that, I think it's exciting that our first speaker in all of this is Ivano. After all that, right? Our fearless leader who has been here a long, long time. I've known Ivano since he got here in 2003. I got here in 2002. He got here in 2003 as an adjunct professor, and he became an assistant professor in 2006 to run the Geologic Oceanography Lab. I'm not going to bring up all the stuff prior to that. Let's just say all of his education was done in a completely different millennium than the 2000s. So I went back to Ivano's CV and checked all of his dates, and it's quite impressive, actually, what Ivano did prior to coming to Moss Landing, which included a little bit of time at UC Santa Cruz, where I know he picked up a lot of networking, which hopefully is coming through on the stream as well. Ivano's done a lot of stuff. I taught geobiology with him, 15 years ago, Ivano. He dealt with deep microbes, coastal geomorphology, and all the fun tools that you can utilize to monitor coastal geomorphology and processes, biogeochemistry, everything that has to do with anything you would call a rock or some kind of inert particle Ivano has either been interested in or involved with. So it's really fun to see him. I want to personally thank him for taking the leadership role in the last year. We haven't seen everyone, and so we've never really gotten a chance to thank him. So I'm going to embarrass him right now by thanking Ivano. No. He wanted to give his own introduction. I said, no way, right? But I do want to thank you. It's going to be a difficult few years in transition in a lot of ways, and I think it's just fantastic Ivano stepped up. And during all of that, teaching a class and making time to come up here and talk to us about his fun stuff. So with that, I want to welcome Ivano Aiello to talk to us about when the fast beats the furious. All right, Ivano, you have to stand up.
So I was 12 when I got my PhD. That's why I'm very young. I know what he's talking about. It's happening. We're back on live. Okay, so thank you all for coming. And I know you're here because of my talk, not because it's in person. And that's wonderful to hear. So first talk is going to be a geology talk, but we're going to talk about diatoms, and mostly when they die. So that's all I care about. Now, the living part that we're going to let it go, and we're going to focus on that stuff. And so today is a story that I presented actually already at the College of Science a few months ago. So I rehearsed the talk once, at least, so you know it's going to be good. And it's a story about something really exceptional that we discovered a couple years ago during my last cruise in the Gulf of California. What you see here is one of my favorite images of the Gulf of California. You can see the Baja Peninsula, and I know I have a pointer. And it's a view from the space shuttle. And one of the things about that you're going to be learning today together is that we look at the oceans and the deep oceans by going out at sea on doesn't change slide. IT, I'm lost. IT, can you hear me? It makes a cool noise, though. So, well, what I was about to say is that when you're out at sea for 2 months at a time, as we do coring the seafloor, it's like being out in space. And there was a very fancy animation that was about to pop up, and I can describe it to you. A ship is going to appear in the middle of the Gulf of California. And you're going to be like, oh, shit. What's happening?
I'm restarting it.
Okay. Yeah, we got it. It's live, so all these problems are. And also, hi to everyone on Zoom. So, and really, being out at sea for 2 months at a time is very much like being out in space. You don't see anything else than the ocean around you, and I love it. I do. And the story is about the fast being the furious, and eventually the story will come together. But first, I need to introduce you to marine biosilica. What's biosilica, and what happens to biosilica once it goes down in the seafloor. And if you look at the slides, you can see there are many things in common here. I don't see Amanda, but I put some sponge pickles there because I knew she was going to be happy. So sponge pickles, diatoms, radiolarians, and some interesting products here, including beauty cream, food-grade diatom earth, and silica gel. So you're familiar, or actually solar panels, and wine. All these things have in common one thing. They contain amorphous silica. And amorphous silica was what builds up the tests of many planktonic organisms, especially diatoms. And amorphous silica, unlike silicate rocks, is made of silica tetrahedra, so there's a silicon atom at the center, surrounded by 4 oxygen atoms, and linked by a covalent bond to another molecule, but is not organized in space in a regular way, regular arrangement, so it's not crystalline, it's amorphous. And that gives amorphous silica different properties, one of them being able to contain a lot of space inside. And in that space, we find water molecules. So in other words, much of the skeletons that make these organisms made of glass with water. Today, we're going to learn what happens after they die and they get to bed as we speak. And that's what marine plankton looks like in the modern ocean. And eventually, the plankton settles, goes through the water column, as many of you know. Actually, you missed the speckles. Actually, much of the siliceous planktons get dissolved in the seawater because seawater are highly corrosive. So anywhere between 1% to 4% actually makes it to the seafloor. And it makes this fluffy stuff that we call the ooze. And then eventually, with time and burial, it turns into that little dinosaur that we call microfossils. So much of what I'm talking about today are microfossils of diatoms. And finally, we call collectively all these diatoms accumulated over time diatom oozes. Okay? So that's to set the stage. And you're actually familiar with many of those deposits that occurred over time because California, that's the reason I'm here actually. I came here originally a couple of years ago from Europe. And to study these layered units here, which crop out in many parts of California because of the very high productivity of surface water that occurred here since the Miocene. So for about 10 million years, diatom had been settling on the seafloors around here. And now some of them popped up because of tectonics. So the original silica in the diatoms is made of, as I said, amorphous silica, which we call opal A. A stands for amorphous. And it's glass plus water. That's the best way to say it. As the sediments accumulate and they get buried by other sediments on top, because of pressure, but mostly because of temperature, there are transformations. The silica starts recrystallizing and form what we call opal CT, which stands for cristobalite and tridymite, which are basically pseudomorphs or different types of minerals as quartz, but kind of made of the same components, which is silicon. And you see now from this amorphous, very porous glass stuff, you get to more crystalline material. And finally, with more temperature and time, everything turns into quartz. This is arguably the most important transformation that occurs in marine sediments because of this. I brought some props, obviously, as a geology talk, rock amber. So this is actually from Toro Road. We just got it with my geology class last fall. So just hear the noise. Very dull. And although I'm super strong, also pretty light. Okay, I broke it. This is opal A. Diagenesis turns into opal CT. So this is the same stuff, but now it's being kind of compressed. Water is almost all gone, and the whole, silica structure turned into a crystalline form. So very different physical properties. This thing can break. This stuff cannot break. Okay, this stuff has a lot of pores, a lot of space for water to be in it. This stuff can't. With more diagenesis, and diagenesis, of course, is a transformation from sediments to rocks, you get into quartz, and that's what you get at the very end. Really hard stuff. And you can find a lot of this stuff all around here. So this happens as sediments accumulate on the seafloor, and they get buried, and over time, I made a mess, turn into rocks, okay? So how do we study that? Well, one way is to go and look at the rock outcrops. But really, the best way to do that is to look at marine sediments as pages of a book. If you're able to stick a straw through them, you can go back on time and actually understand how this happens over time as sediments get buried. And we do that by using drilling vessels. You see here with the first one that was used for worldwide operation starting in the 60s, which is a Glomar Challenger. And really, what you see there is a derrick with a big straw, with a big pipe. That's a wide line that goes all the way down to the seafloor. And then eventually we poke the seafloor and we collect the sediments and the rock from the seafloor. Now, it sounds easy, the way I'm saying it, but it's actually very complicated. And just to let you know, this is part of what it's called, right now it's called the International Integrated Ocean Discovery Program, which is a program that started earlier in the 60s. And in the last 50 plus years, has been poking the seafloor all over the place in the world. Some of it was mostly to confirm or establish the theory of plate tectonics. That's how we know how plate tectonics work, but also to understand hazards in subduction zones, life in marine sediments, and especially paleoceanography, which is climate change over time. That's how we can actually model future climate change. And there are different interactions of the program. Right now, we are in the 2013-2023 phase, actually it's about to end. And the newest ship is the JOIDES Resolution, and I just calculated I spent almost 1 year of my life on this boat. Yeah, and just to tell you, your life is in this box here. Everything else is pipes. That's what they're talking about. Because, and by the way, this is a big ship. It's bigger than the Martin for sure. We're talking about, what is it, 270 feet long vessel. It's a huge ship, but as I said, science, sleeping, eating, and all the other amenities of life, they're all occur in this little tiny box here. Very exciting. So the point is that we use a very long straw, actually a wire line, with a straw attached to it, to poke the seafloor, and different types of drill bits, and I brought you some props here. This is what you're looking at in the upper right. These things here rotate and drill through the seafloor, and this thing here actually has a piston coring action, so we can actually collect fully preserved sediment cores from the seafloor, if the sediments are soft enough. Otherwise, we have to drill the whole thing, obviously. And the amazing thing about this boat, which, by the way, is from the 70s, so everything is 70s style, which means we can fix it on board. We can go out for 2 months. Everything can be either fixed or made on a ship. We are sitting sometimes for, say, weeks at a time in 3,000 meters of water, poking something that's this size on the seafloor. It's crazy. And storms come through, and anything that happens, and we keep going for days and days at a time. It's just amazing how this is even possible. The other thing that is important to our talk, my talk, your talk, is not only collection of cores, but also the ability to measure temperature, pressure, and other physical properties on site. So we can actually put probes in the sediments down to hundreds of meters and actually measure the condition there. This is actually really important because we weren't able to do this until earlier because that's the technological development that's more recent. So we collect sediments and we study, and we can actually account for the physical conditions in place, okay? Technology has evolved in the last few years. This is a beautiful picture, and I want to take a second to recognize and thank my advisor, actually, Bob Garrison, who passed away a couple months ago. And he's really a wonderful human being. Actually, we are seeing here, those are the fathers and the mothers of modern marine geology. This was a cruise in the Mediterranean by the Glomar Challenger in the 70s. That's when they discovered that the Mediterranean actually desiccated in the Miocene. I don't know if you ever heard the story. The whole basin evaporated. So that was the cruise actually that discovered that important fact. And Bob Garrison was my advisor at UC Santa Cruz, and he's the father of the Monterey Formation in many ways, and the first one who understood the significance of this unit. So thank you, Bob. Now, things have changed. But, I mean, also, notice, technology, scale, coffee, and the color chart. That was it. Now we are talking about a super fancy, highly advanced series of labs, geochemistry, physical properties, musical properties. This is me with my red hat, Tim Sisu style. So it's a very different ordeal, and we do everything on board. As we get out of the boat in 2 months, we write books on our cruise. Everything is get published right away. So it's really, really intensive, but wonderful. A lot of interdisciplinary research. Lately, in the last 10 years, we have a lot of microbiologists coming to our cruises to study life in extreme environments. So it's a super exciting place. And as you core, history comes to you every minute. So you're constantly exploring. My point is that, so my first cruise was in black and white. And my point is that what you see today is the result of the work of dozens of people. So the ship hosts pretty much 150 to 200 people. Crew, everybody is collaborating. So it's a wonderful, wonderful experience from all over the world, by the way. Okay, so what happens to diatoms after they go to bed? It's true. So what we understand about silica diagenesis, again, diagenesis is transformation from the biosilica, which is the silica that's precipitated out by diatoms, sponges, and radiolarians, is that the transformation from silica, biosilica to crystalline silica is a dissolution precipitation process, which is you start with this beautifully shaped diatom frustules here with a lot of nice detail in the SEM, and eventually the diatoms, the skeletons, start exuding silica gel, colloidal silica, which makes these bonds that are called siloxane bonds. And the bottom line is that this molecule polymerize, and they have a net negative charge, surface charge. So if there are catalyst factors, such as this lovely MHC, which is a metal hydroxide, such as brucite or magnesium hydroxide, those cations allow silica to actually precipitate and crystals to form, such as this opal CT crystal that has this really unique series of blades, which are part of the crystalline shape. So this is it's a microcrystal. We're talking about a few microns. So we understand that silica comes from, the precipitation of silica comes from the dissolution of diatom frustules or radiolarians. We also know that the range in which this transformation occurs, the temperature range, temperature is the main driver of silica diagenesis. It's pretty narrow. Well, I mean, it's not narrow because it starts at 2 degrees Celsius, but it has been documented as high as 56 degrees Celsius, which to you doesn't mean anything really. It's like Celsius, but actually 56 degrees Celsius in marine sediments is pretty high temperature. However, one thing I want to point out is this. So far, our understanding of the temperature condition of silica diagenesis was mostly based on either laboratory studies, modeling exercises, or proxies, such as delta O18. There are very few studies and evidence as to what is the temperature of silica transformation in situ, in place. Because it's so hard to go down there, kilometers of water, kilometers of sediment, or hundreds of meters, and measure temperature, right? You're sticking a thermometer in the deep subsea floor. But when we started this cruise, looking at silica and diatoms in the record of the Gulf of California, I left with the idea that we were going to find maybe the highest temperature we were going to encounter was going to be 50 degrees Celsius for this to turn into rocks. That's what I'm talking about. Why this has been studied in the past? Because I was telling Brian, much of the oil in California comes from siliceous deposits such as diatomites of the Monterey Formation, by the way. So much of the oil that you put in your car is actually coming from the dead bodies of diatoms who patiently died over the last 10 million years. And now in about 20 years, we are delivering all the carbon back to the atmosphere because we're very efficient in our way to destroy the planet. So the other thing that we know about silica diagenesis is that, mostly through experimental data, is that it is controlled by temperature and the concentration of dissolved silica in pore water. So there's going to be a lot of chemistry today. I apologize. And so this graph here shows the field of existence of the three main phases of silica. Again, opal A is amorphous, opal CT is this crystallite, tridymite phase, and finally quartz, which is the most stable phase. And if you notice, all these fields are outlined by lines which grow with temperature and dissolve silica in pore water. So this is the interstitial pores of the sediments, and that's the silica, dissolved silica in the sediments. So in other words, to have this transformation occurs at higher temperature when there's more dissolved silica in the pore water. The other thing that we know about, well, we thought we knew about silica diagenesis is that if you put together all the collective record of places in the subseafloor of the oceans where the amorphous silica turns into crystalline silica, we see this type of trend here, which is that the lower is the temperature, that, the change in temperature with depth and the sedimentation rate, so how fast the diatoms are accumulating, the longer it takes to amorphous silica to turn into crystalline silica. So look at the numbers here. In some places in the ocean, it takes, 13 million years for the diatoms to turn into rocks, because temperatures grow very, very, very slow with that. So this is the cold places of the seafloors of the ocean, where the temperature gradient is very low. However, there are places in the ocean where the temperature and the sedimentation rate are really high, and amorphous silica turns into crystalline silica in only a few million years. In the Gulf of California, where, as you will learn together, both sedimentation rates and temperature are incredibly fast, we were expecting to find silica from amorphous to crystalline right below the seafloor. That was our expectation. That's what we set out to find, okay? And of course, we didn't. That's the whole point. The fast. So why the fast and the furious? Because it's a catchy title, but also because there is a meaning behind it. The fast is the productivity and the delivery of biogenic sediments in the Gulf of California. To give you a sense, it takes about 1,000 years, I think in 1,000 years, I don't know why, to make 1 meter of sediments in the Gulf of California. If you go in the open ocean conditions, it might take 1 to 10 million years to make the same amount of sediment. In other words, the delivery rate and the ability of biosilica to accumulate in the Gulf of California is orders of magnitude higher than in much of the rest of the world's ocean. Very highly productive waters, because they are very highly productive waters. It's a winter satellite image from the Gulf of California. So that's the fast. The furious is the tectonics of the Gulf of California. So as you all know very well, the Gulf of California is the result of the interaction between the San Andreas Fault system and the North American continent. And it's very much like a zip thing that opened up the western margin of California, of the North American continent, and is moving Baja Peninsula and much of California to the north, and the rest of North America is going to the south. One of the results of this strike-slip tectonics is the opening, the stretching of the continental crust and the formation of oceanic crust. Now, when we went out there to measure the temperatures using these logging tools I showed you about, we set out with this idea, which is if you measure the change in temperature with depth in continents, which is called the geotherm, it takes about 550 kilometers to get to about 500 degrees Celsius, okay? If you go in the oceans, because there the crust is thinner, it actually might take a little less. Say that you get to 500 degrees in about 20 kilometers. You see what I'm saying? We went in the Gulf of California, and there, the geothermal gradient is 1 order of magnitude higher. So you get 500 degrees Celsius in 1 kilometer. It's insanely hot, which means that once you start coring, it gets really, really hot really, really fast. The other thing that's really important for us to understand, which was also a major breakthrough before the cruise, actually, that's one of the reasons why we went out there, is that, if you took my classes, you've seen this slide before. This is how baby ocean forms. And the Gulf of California has always been an example of baby ocean. You have this asthenospheric rise, which is the mantle rises. You have mid-oceanic ridges, everything gets pushed away, and here's the ocean forming. recent seismic profiles show that actually this is not true at all. What they show is that much of, if you look at the, sorry, I have animation. If you look at the spreading center, much of the magmatic activity actually occurs widely dispersed across the whole basin. So, in other words, the magmatism is not just fixated or into the axis, but actually spreads all around in the form of intrusions of magma that we call silts. This all, this red line here outlines the seismic profiles that shows this intrusive bodies, which is mostly basalts, basically, moving all across the basin. So that was a very different understanding. Our goal was to understand what happens to this. No, that's me. Our goal was to understand what happens when you have sediments that have been intruded by the magma, not intruded. You see these two sites here. This is a seafloor. Those are drilling sites. One right an intrusion, the other one next to it. And then also when these intrusions are very shallow compared to the seafloor. This is seismic profile mean sound, so it's not really a picture of the crust, but it's very close to it. So these three sites here, which are, that's what we call location where we drill, 45, 1546, and 1547 are the ones I'm going to be talking to you about today. First core on deck. I'm happy. This is actually the first core on deck that we got during that cruise, and everything is this color here because that's what the diatom sediment looks like. Even my hat is the same color, as you notice. Those are, and actually it's kind of cool because you can see the burrs here. This is the seafloor, basically. We're poking the very top ooze of the seafloor, and then you can see all the lamination and other features that are typical of diatom-rich sediments in an anoxic basin. Actually, the oxygen content of the water is very low. We drilled the three main sites, and I'm just giving you an overview. And what we found is that if you go back on time, and time is depth, so those are hundreds of meters. This is a half a kilometer, 550 meters, 200 meters. Those are the three sites I mentioned earlier. What we found is that if you go back on time and depth, the whole thing here, it's diatom oozes, diatoms, because that place has been productive forever. However, the color change here displays changes in physical properties, which is that at a certain depth, diatom oozes go from this to being this, from being soft sediments to rocks. And surprisingly, we found that this transition occurs very deep below the seafloor, not as shallow as we were expecting because of very high temperature gradient. You see what I'm saying? So we found that sediments are really soft, really deep. The other thing that was really interesting to find, actually more than interesting, is that there are magmatic intrusions, some of which are hundreds of meters thick. So there's a big magma body, which seem not to actually do anything to the silica itself. So we thought that those hot body of lava, well, intrusive magma, which are 1,000 degrees Celsius, would have cooked the whole thing. But actually, it's quite the opposite. So I was really scratching my head really hard because I couldn't understand what was going on. Today, maybe we're going to figure it out together. So that's what, so you see Opal A, again, is amorphous silica on top. Opal CT is this harder, more brittle cristobalite, tridymite silica below. That's what they look on the core table. I mean, you can see the difference yourself. This is a beautiful laminated diatom ooze, kind of fluffy. The lamination is a beautiful example of El Nino scale cyclicity. And then you get into the Opal CT, and you see how broken up everything is. Actually, it was full of oil, too, because you have a lot of space for oil and gas to accumulate. That's what oil companies really love to find. So very different characteristics. The last 2 years have been a wonderful exploration of the sediments and samples that I have here in my lab, using different instrumentation. As you know, we have really cool instruments here. One of them is our brand new X-ray diffractometer, which, to make a long story short, allows you to identify the degree of crystallinity of anything. Could be a sediment, could be a shell, a test, could be a pharmaceutical product, any polymer, using the principle of the Bragg's law, which is using X-ray diffraction. So this is an X-ray source. This is a goniometer. It's a thing that rotates. So you're constantly bombarding the sample with X-rays from different angles, and it's safe, by the way. And then you have a detector that measures the intensity of the diffracted radiation. Now, this little cartoon here shows the basic principles, which is that there's a relationship between the angle of incidence of the incoming X-ray radiation and the angle of reflection, so to speak. It's not a real reflection because it's X-rays. You're exciting the electrons in the atomic structures, and the spacing between crystallographic planes. So you can measure the distance between the layers of the atoms within a crystal. So you can tell how thick, and we're talking about nanometers, how thick those layers are, and how crystallized the stuff is, right? Long story short, it's a very simple relationship, actually, but it's a super powerful tool. Also, I'm making it simple. So we can make what are called diffractograms, and I'm going to skip some of the details here, but I just want to show you this, which is when you have amorphous substances like opal A, the crystals are not formed. So they're all kind of scattered. So what you get is a very broad curve like this. Go back. It's a very broad hump. There's no clear crystalline structure. However, as the crystallinity increases, the diffraction becomes more and more relevant. And you can actually measure the spacing of the crystals. So you can measure the degree of crystallization this way. It's really cool. And those are examples from my Excel spreadsheet of what I'm talking about. Those are the blue lines you see here. Those are amorphous crystal. So there's a relationship, as I said, between the angle of incidence and the spacing. So we measure everything in what is called 2 theta, which is the actual angle of incidence. And as you notice, the opal A makes this kind of broader peak. There are other minerals here, so it's more complicated. And then eventually, as the crystallization continues, the peak becomes more and more narrow and taller. So we can measure that as proxy for crystallinity. Is it making sense? I hope so. So here's some results. It's like a thesis defense. Here's my results. Those are different X-ray diffractometric profiles stacked. Not in depth is actually from bottom to top, deeper, shallower, actually stacked in relative temperature. So this is a temperature scale here. We start from 70 degrees Celsius, which is already telling you we are way above the 50 degrees Celsius I told you earlier. That's where we're getting to, all the way up to 120 degrees Celsius. These are in situ measurements. We measure the temperature there. It's not a model or anything else. And as you notice, if you keep your eye on this gray purple band here, that's where the silica peak is. And initially, there's a very broad hump, and then eventually you see a baby one, and then it gets more and more prominent until this one here has a really like sharp shape to it. So you can measure that in 2 ways. One is and of course, the big deal here is that the first time we see amorphous silica turn into crystalline silica is happening at 77 degrees Celsius. That's way higher than anything else that's been ever reported before. 50% higher. So it's insane for us, for me. One way to describe that is by measuring, one, the position of the peak, which is reflected by this spacing here, which is basically where the peak sits in relation to the incidence angle of the X-ray diffractometer. And the other one is the peakness of the signal, which is described as the full width height maximum. So what this is showing essentially is that as the peak gets narrower, it starts moving from the left to the right. So there's a shift in the position, which reflects the fact that the layers between, the atomic layers are getting closer and closer together. So everything is getting kind of compressed, more crystalline. So this is happening. Everything is turning into this stuff that goes bang. You see, that's where the noise is coming from. The other cool thing is that we have measurements of temperature in place, so we can correlate for the first time, for the first time, empirically, with field data, the spacing, the crystallinity with the temperature. So we can create what is called a paleothermometer. So by looking at the spacing, we can actually tell which temperature the silica was in, which is amazing because we can do it elsewhere in the world, right? So that's going to give us a new tool to investigate the temperature which sediments, siliceous sediments have been subjected to. Okay, so let's take a break. No, not take a break, but let's take a big breath, because this is a complex diagram, and there's no way for me to get out of here, otherwise the story doesn't come through. So this is from a paper, obviously. And I'll do my best now to spend the next 2 hours here, but I'd really like you to get the gist of it, which is, on the left side is, so first of all, those two plots here show depth in hundreds of meters, so 0 to 600 meters, for two sites, sites 15, 45, and 46, which are, if you remember, they are located right at the edge of this intrusive body. One of them, 45, is actually outside the intrusion, so further away from the magma. And 46 actually includes the intrusion. And you can see, and the colors here reflect these two sites. Red is 45. So everything is red here at site 1545. Everything is green at site 1546. And if you notice, there's a sill. There's this intrusive body right inside 1546, which is 100 meters thick. Big stuff made of magmatic rocks. The green line describes the depth at which we found this transition from amorphous silica to crystalline silica. In site 1547, which is in a place where there's much higher geothermal gradient, the transition occurs much shallower. You see 300 meters, around 320 meters here, around 120 meters here. And there's another sill, another intrusion, which is shallower, as you can see here from this picture, okay? The x-axis has 3 different parameters. That's why it's one of those crazy diagrams that, you know, that's what you do when you try to get published. One of them is temperature. So those are in situ temperature, from 0 to 100 degrees. And these lines here describe the change in temperature with depth. In other words, at 300 meters, we measure about 70 degrees Celsius. That's pretty clear. If you notice, when you look at site 1547, you get to the same temperature, much shallower, around 100 meters. So 100 meters of sediments, and you get to 70 degrees Celsius. That's the place where probably one of the hottest places in the planet. I mean, unless you go on magma chamber and where volcanoes are exploding and stuff like that, but you don't want to go there. The other parameter is pore water silica. How much silica is in the pore water, in between the sediment particles. And if you notice, the silica profiles do kind of the same thing, which is the amount of silica, this is in micromolar, increases with depth. That's because the diatoms are shedding silica to the pore water until to a certain point in which they start actually going down again. So something is taking out the silica from the pore water, which coincidentally happens where you have this conversion, which obviously is related to the diagenesis of silica. This is actually textbook stuff. And the same thing that happens here, just shallower, okay? Finally, the last parameter, which is down here, is the degree of crystallization measured with X-ray diffractometry, which shows that as you go deeper, and by the way, those symbols start here because that's the place where we actually start finding opal CT, the crystalline phase. And if you notice, as you go deeper, the crystallization increases with depth. Is it kind of making sense? Thank you, because I know it's like a full stuff here. But the cool thing about it is that it puts together all these different processes, which is temperature, which is the change in pore water concentration of silica, and the place where silica precipitation and crystallization occur. The most important thing to observe are, first of all, that this thing here, this conversion from opal CT from amorphous to crystalline silica occurs at close to 80 degrees Celsius. Again, this is a completely different temperature setting that was ever reported or even conceived with models, especially kinetic models, which is my the next part of my talk. And the other one is that if you notice one thing, which was crazy, is that the sill, the intrusion, splits this diagenetic sequence, but it doesn't affect it. In other words, the two sides that are next to each other have the same degree of crystallization. The sill, the intrusion, seem to come later, after the crystallizations occurred. And that's a hint to say that probably follow that boundary, because if you are an intrusion, I'm sure you are, and you're moving through rocks, this is going to be all fractured and you move very easily. When you get to the soft stuff, you kind of start spreading laterally because it doesn't break through. You see what I'm saying? So physical properties are very important for this process. Thank you. All right. And, you know, this is what I just talked about. I forgot I had all this fancy thing. So let's look at some cool photos, because that's what we're here for, I'm sure. So this is what the sediments look like at 5 degrees Celsius, we are very close to the seafloor, beautifully preserved diatoms, frastules, with all the ornaments, everything is just beautiful. We go now, some detail about that. Also, it's just lovely to see those pictures. Now we are at, now I skipped the whole thing. No, now we have 72 degrees Celsius. So the temperature here shows the in situ temperature. So we are about 22 degrees Celsius higher than anything reported before in terms of preservation of silica. You can still see the diatoms really well. Look at all these little tiny features. They haven't dissolved yet. They're still there. They're fragmented, so they're shedding silica, but they haven't reprecipitated anything. Now we are increasing the temperature with 77 degrees Celsius. The diatoms are still there, but when you start finding out these little blobs here, which we identified as opal A prime, so essentially those are amorphous precipitate of silica. But the bottom line is that there's no transition from this to actual crystalline phase, per se. Only when you get to higher temperature, now we are around 100 degrees, you can start seeing those little bladed things. You see those little fur balls, they're all bladed. That's the opacity we were talking about. So between 80 and 100 degrees, that's when the transformation occurs. And eventually, the deeper you go, everything is gone, and that's quartz. So those used to be diatoms. Now they're, the red rock I showed you earlier. There's no any left over. So we were talking about this, right? We were expecting to find the shallowest occurrence of opacity, everything turned into rocks, very shallow. So what's happening here? It just makes no sense. So the kinetic models that we have for silica diagenesis just don't match the real-life examples. And now we are going to talk about our handy-dandy Arrhenius equation here, which is the equation, as many of you know, that describes the transformation rate of kinetic reaction of the first order. So we're simplifying the system. First order means the transition from opal A to opal CT as a first order kinetic equation. And essentially, the Arrhenius equation relates the rate constant, which is the frequency of collision, so how likely is for the diagenesis to occur, to temperature. So the higher the temperature, the faster this will happen, and is controlled by two parameters. One of them is the activation energy, which is essentially how much energy you need to start it to go in that direction, and the pre-exponential factor, which has to do with the actual molecular structure of the components involved in the equation, in the reaction. If we use classic kinetic models, and when I mean classic from the 60s, so they've been used for the last 50 years, and we calculate, which I did before going on a cruise. I was expecting to find this transition, so those are the three sites, to find the transition to occur between 47 and 53 degrees Celsius. That's what the models would have told me, which is about 100 to 200 meters shallower of where it is now, instead of 79, 77 degrees Celsius. So you see the difference between expected and measured. Not only, but according to the kinetic models, the sediment in which the transition occurs should have been much younger, 200,000 years, not 400,000 years or so. That's the discrepancy. So what's wrong with that? That's what I've been trying to figure out in the last couple of years. And one of the ideas that maybe the kinetic models are not working. Now that we can actually measure the temperature, let's try something else. So what I did, you got that. So you can take the Arrhenius equation and you calculate the logarithm of the rate constant and the right side of the member here, and turn it into a linear equation like the one you see here. So it's just a logarithmic transformation. And it turns into a linear equation. You see, this is the y, this is the x, and this is the intercept. And actually, if you know the temperature and you know the timing of the silica transformation, or any chemical transformation, you can actually derivate the activation energy and the intercept. So you can calculate those parameters. That's what I did. I got data sets from the only 3 places in the world where people have collected opal CT and measured the temperature. It's not a lab setting, it's not a model. And obtained these 2 parameters here, which is EA and A. And so what it turned out, and that's the equation, I mean, pretty simple stuff, but basically what it turns out is that according to the actual empirical data, the transformation rate is much slower than previously thought. So when we use these new parameters, now the calculated temperature using the new kinetic model is much closer to the real one. So in other words, the kinetics of silica transformation, at least in these settings, could be much, much slower than previously thought. So there are implications of that, of course, which I'm here to discuss with you in the next 5 minutes. And the beauty of this is that you can start modeling things, and those are some of the modeling results. So you can actually see here how when you apply the classic, so this is the same figure you saw earlier. This is just a model that shows how when you use the classic kinetic parameter and you model temperatures with that, you would expect to find this interception between the geothermal gradient and your modeled parameters at about 200 meters below the seafloor. Rather, when you use the new parameters, they're actually right on the spot of where do you find the transformation. So the new kinetic parameters work not just for the Gulf of California, but also for the Bering Sea and the Sea of Japan. So not just one basin. And this is the same example for the other side. The other, and I'm almost done, believe it or not. The other cool thing is that you can use this model to play God and say, well, what if the sedimentation rate weren't as fast as they are? What if they were an order of magnitude less? Actually, what it turned out to be is that if you play with the Arrhenius equation and you assume that your sedimentation rate were about 20% lower than they actually are, actually the older classic model accounts for the temperature at which the opal CT transformation has occurred. In other words, it looks like it's the burial rate. The burial is so fast that it gets the diatoms through this temperature window really fast. They don't have time, so to speak, to turn into crystals. Does it make sense? It's not, I mean, it's the slow kinetic. It's not really, I mean, you know, really it's the kinetic that's slow, but that's what happens. You're shuttling this, diatoms through a really hot place very fast. I mean, 1 meter per 1,000 years is fast as far as concerned geology, even biology. So what have you learned? What I just said, that biosilica transformation, so opal A to opal CT, could be much slower and it can occur at a much higher temperature than previously thought. That we need new kinetic model to account for silica diagenesis that are based on empirical data. Now we can actually measure things in the field. And we also learned that this transformation has big implication for the structure of the shallow crust. And actually, we learned that possibly magma might actually be routed by this, might be diverted by the occurrence of this boundary. And here I have a little model I want to share with you, and then I'll take some questions, okay? So this is actually, we're talking about the old times. You remember, Mike, when there was the whole thing going back and forth between Greg Caillet and my predecessor, Gary Green, about biology controls geology or geology controls biology. So they were going on, every talk was like, oh, so that's an example in which biology. So in this case here, did biology beat geology? So did the fast beat the furious? So the fast being the fast sedimentation rate and the furious being the magma. So this is a conceptual model I've been working on and I'm sharing with you, which is a way to look at these two main processes, which is temperature and burial rate together. So this is a source of heat. So the red here describes a typical magma rise, which is very symmetrical, so it gets hotter as you go away from the center. However, the surface here, this is the ocean, this is the ocean top, this is the seafloor, and because of upwelling, this side here, the left side of the diagram, gets more diatoms. So sedimentation rates are faster. So in other words, faster sedimentation rate here, slower sedimentation rate here, equal heat distribution on both sides, okay? So we take a ship out there. This is the long straw we were talking about. Those are our sites, site 47, 46, and 45. 47 is a much hotter place than the other two, and 46 is within the intrusion, as you learned earlier. Based on the model that we have, we are expecting to find what? That the transition between soft sediments and rock occurs shallower where there's more heat, but also shallower where the sedimentation rates are lesser because the silica is not shadowed fast enough through the temperature window. Does that make sense? So our boundary, which again is a huge change in its physical properties, no water, brittle rocks versus soft rocks, occurs shallower where you have lower sedimentation rates and higher heat and deeper otherwise. What we found is that if you start looking at the system together, I don't know what's next. Yeah. The intrusions, this magma routing, seems to be actually intercepting this boundary. This is dashed because it moves over time. So there's a simulation that basically occurred about 50,000 years ago. In the meantime, the whole thing just moved up. But essentially, the story here is that the intrusion, because, again, this contrast between brittle, broken up rocks and soft sediment, it moves up and then eventually spreads laterally. And we have numerous examples of that in the rock record, which makes you think something. Have you noticed how the Gulf of California doesn't have volcanoes on the seafloor? It's all sedimented. There's not like a spread, it's not like the mid-Atlantic ridge or other places around the world in which there's a volcanic building at the center of the ocean. It's all clogged with sediments. The idea that we're working on is that that's the result of the really fast sedimentation. So the fast sedimentation is moving this major discontinuity further down and is capping the lava from coming out. In fact, if the productivity changes, then you might surmise that the actual boundary, the change, I know, that's a really fancy animation, that the sediments turned into rock much shallower, which means that the magma can actually make it all the way out and actually build up volcanoes. So that's the mind-boggling correlation between primary productivity and the way an ocean can form. So that's kind of the story together, the fast, the furious, and the control on ocean tectonics. I have one more slide, probably your favorite. I want to thank you for listening, and you know what's next. Thank you so much.
So a couple more comments before he takes questions. Students who did come in late, just remember there's a sign-up sheet here for your attendance. Second, beer is outside. So when Ivano calls it quits and wants to take the discussion outside, just make your way on out there. And if you brought your own mug, great. If not, there are cups there as well. And then third, for questions, we're going to try and do in-person questions first. So feel free to just ask those questions. Ivano's going to try and repeat the questions so those on Zoom can hear it. For those of you who are on Zoom, if you would like to ask questions, just put it into the chat, and Ivano will answer it from there.
Yeah, I can't find the chat, but yeah, absolutely. I'm looking for it.
Okay, well, maybe Laura can help with that. But does anyone, and then Ivano wants to take control of the questions, so it's all him.
I'm in charge. Here's the chat. Okay, guys.
We got one here, Ivano.
Hey.
You spoke a little bit about marine geology technology in the 70s versus now. What do you think the future looks like, and is there any technology coming online that you're especially excited about?
Yeah, so the question is about, I don't know if anyone is there, but the question is about future technology in deep sea drilling, right? So the ship, the JOIDES resolution after more than 30 years, actually more than that, is going to be dismissed in a couple of years. And it's going to be missed because we don't have a replacement for it yet. So there are plans to develop a new vessel, which is going to be, technologically more advanced, obviously. The cool thing about the JOIDES resolution, you can really fix it on board. There's another vessel, drilling vessel, that the Japanese colleagues made. It's called the Chikyu, about 10 years ago. Actually, it was damaged during the Fukushima earthquake. And that thing is super technological. It breaks every day. It's like constantly, so as a line of helicopter bringing parts. The JOIDES resolution takes off back in 2 months. So the nice thing about simple technology is that it's cheaper to run and can be fixed. However, what's changed is the science stack, the science that we can do on board. That's really, the drilling technology is really sticking a pipe in the sediments. And so I think it's going to stay pretty much the same. There's more details, but we don't know where the new vessel is going to be built, though, because it costs a lot of money. And to operate, we're talking about anywhere between $100,000 to $300,000 a day. That's what much it costs. So one of my samples, if you actually budget it, it's a lot of money. Yeah. Mike.
Yeah, so Ivano, early on, you kind of set the stage for why the wine space was so interesting to you, and it led to this understanding that these models weren't necessarily, as accurate or as useful, and you were finding some changes to kind of your perception in regards to the dynamics. Is there anywhere else on the planet you'd like to go that has either similar interesting features that might yield it, or is just similar to Guaymas and hasn't really been looked at yet? Are there other places, or is it really just a special place? And then how does that reflect our models, our global models? If they come out of a very special place, how general are they?
Yeah, so the question is whether Ivano Basin is the only place where you can find, this really unique combination of high sedimentation rates and of diatoms and the high heat flow. There are other places in the world's ocean. So the answer is yes. Two of them are the Bering Sea to a certain extent, and the other one, which are also very biosiliceous. There's a lot of diatoms. And the other one is the Sea of Japan, which is very similar to the Guaymas Basin. And luckily, we had already a lot of expeditions there. And I actually applied for funding. See, please fund me, to actually get sediments from all these basins. So the nice thing about the ocean drilling program is that anyone can access not only the data that are collected on board, but also the samples. So that's one way. You don't have to go out there. I mean, people already collected the samples that you can use. And luckily, it's not living stuff, so it doesn't deteriorate over time, really. So you can look at things that have been collected years ago. In terms of new cruises, really, to give a sense, the Guaymas Basin was investigated in the 80s by actually many people from Scripps, who actually built most of the models we know about silicate diagenesis. But they weren't doing, their ability to recover sediments because the technology was very limited. And also they were fixated on the axis. Because they were trying to understand how the ocean works there. So now we're learning more about the actual tectonic evolution of an ocean, we start looking at things away from the axis. So we can go back to basins that have been already investigated, but in different places. So I'd like to go back to the Sea of Japan, for instance. That would be another place where I would go back. Finally, a little pitch about geology. This is actually a piece of Franciscan Formation. This is from San Francisco, from the Golden Gate Park, from the Marine Headlands, sorry. So it's not just the basins today, but also the ancient oceans that have disappeared. So there's a kind of an understanding of how the planet has evolved and how life, primary productivity, has controlled the way oceans have evolved over time. I mean, I think it's crazy fascinating because I'm working on diatoms and siliceous organisms, but actually there's carbonates too. They also have a different way to turn from sediments into rocks. So there's a whole, I think, direction of research in which we can really understand how life, primary productivity in the oceans, and the oceanization, the way oceans form, have kind of worked together. Does it make sense? It does. So if you want to fund my research project, I'll be very happy.
There may be some on.
I'm trying to. I see Jim Harvey, but I don't see the chart. This is the first time we're doing. First of all, oh.
Were you able to hear me? I was the one asking the question.
Oh, thank you, Amanda. I think everyone can hear actually. Do you wanna say it yourself?
Where are you, Amanda?
You were here, by the way. What are you doing there? Thanks, Ivano. I learned so much. Thank you. I was interested when you were describing the opal A to opal CT transformation and how she got muted. Amanda got muted, which is terrible. You don't want to mute Amanda. I'm going to read.
Thank you.
Oh, you're back.
Thanks for this question. Yeah, sorry, I had to leave the room and I didn't want to come back in and interrupt. Yes, so that when you were showing the opal A to opal CT transformation, you talked about a hydrogel forming in the pore water.
Mm-hmm.
How is that affected by the properties of either the sediments or the pore water? Like, I'm guessing oxygen would matter in its formation, but does the grain composition or pH matter too?
Excellent question. Excellent question. Thank you. Yeah. So there's a lot going on, right, which I totally skipped on because. So one thing is that what the experimental data showed that the size of the particles is important because of the surface area. So the more surface area, the more reactivity. So if the diatoms are more broken up, they tend to turn into rock faster because they're more reactive, right? That's typical of any system. And the other one is the presence of clay minerals. So some clay minerals, like smectites or montmorillonites, which are very common around here, they suck magnesium. and magnesium hydroxide. So it's been shown in the lab that the presence of clay minerals might delay the transformation of silica, right? However, what we show is that this delay, at least in experimental conditions, is only a couple degrees Celsius, not 50. In other words, if you add clay, this reaction is delayed about, a couple degrees Celsius. But what we were finding is that that change is much, much larger. So those are the two main things. The pH, higher pH facilitates the silica transformation, but really doesn't have a big role. Yeah, is this making sense?
It is, and can I follow up then? It sounds like you could actually, I mean, there are two processes. There's the dissolution going on, and then there's the new CT, opal CT formation with that hydrogel. So, I mean, do those processes often get decoupled? Or are they kind of going to happen in concert? You know, I'm thinking of diatoms or sponge spicules that would be dissolving, right? And so the dissolution rate could be the limiting step, or it could be the hydrogel formation into the opal CT.
Yeah. So the process occur at the same time, right? And that's what I show you in this diagram, showing how the dissolution increases over time. So now the question is, when is it detectable? Because one of the things, I skipped in a lot of details because otherwise, really, we're going to spend a couple of days here, is that when is that you can actually see it happening? So that's why we're using scanning electron microscopy, X-ray diffractometry. But if you notice, one of my slides, I put 10%. So I'm using a 10% occurrence of opal CT as a threshold when it's detectable. But this process might occur earlier. It's just not detectable. So I don't know. I don't know if that's the answer to your question. But most likely, the two things occur together. However, silica dissolution occurs right below the seafloor. So if you look at any pore water profile from pretty much any part of the world's ocean, you're going to see him. Now you're going to see this. Well, you're going to see that the silica in pore water silica start increasing with depth right below the seafloor. So the dissolution process occurs much earlier than the precipitation process, for sure.
Got it. Okay, thank you. Yeah, really cool.
Yeah, but you see here I put 10%. I forgot to point it out but that's the detection limit, Yeah.
All right, Ivano.
Yeah, let's get some beers. Thank you so much for coming. Thank you, Amanda.